Solution Center in partnership with World Bank Group. Today's webinar is focused on the introduction to Global Wind Atlas. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or over the telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. Doing so will eliminate the possibility of feedback and echo. If you choose to dial in by phone, please select the telephone option, and a box on the right side will display the telephone number and audio pin you should use to dial in. If anyone's having any technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you'd like to ask a question, we ask that you use the question pane where you may type in your question. The audio recording and presentations will be posted to the Solution Center training page within a few days of the broadcast and will be added to the Solution Center YouTube channel, where you'll find other informative webinars as well as video interviews with thought leaders on clean energy policy topics. Finally, one important note to mention before we begin our presentation is that the Clean Energy Solution Center does not endorse or recommend specific products or services. Information provided in this webinar is featured in the Solution Center Resource Library as one of many best practice resources reviewed and selected by technical experts. Today's webinar agenda is centered around the presentations from our guest panelists who have joined us to introduce the Global Wind Atlas. Before we jump in, I'll provide a quick overview of the Clean Energy Solution Center, and then following our panelist presentation, we'll have a question and answer session where the panelists will address questions submitted by the audience. And then at the end of the webinar, you'll be automatically prompted to fill out a brief survey, so thank you in advance for taking a moment to respond. The Solution Center was launched in 2011 under the Clean Energy Ministerial. The Clean Energy Ministerial is a high-level global forum to promote policies and programs that advance clean energy technology, to share lessons learned and best practices, and to encourage the transition to a global clean energy economy. 24 countries in the European Commission are members, contributing 90% of clean energy investment and responsible for 75% of global greenhouse gas emissions. This webinar is provided by the Clean Energy Solutions Center, which focuses on helping government policymakers design and adopt policies and programs that support the deployment of clean energy technologies. This is accomplished through support in the crafting and implementing policies related to clean energy access, no-cost expert policy assistance, and peer-to-peer learning and training tools such as this webinar. The Clean Energy Solutions Center is co-sponsored by the governments of Australia, Sweden, and the United States with in-kind support from the government of Chile. The Solutions Center provides several clean energy policy programs and services, including a team of over 60 global experts that can provide remote and in-person technical assistance to government and government-supported institutions, no-cost virtual webinar trainings on a variety of clean energy policy topics, partnership buildings with development agencies and regional and global organizations to deliver support, and an online library containing over 5,500 clean energy policy-related publications, tools, videos, and other resources. Our primary audience is made up of energy policymakers and analysts from governments and technical organizations in all countries, but we also strive to engage with private sector, NGOs, and civil society. The Solutions Center is an international initiative that works with more than 35 international partners across a suite of different programs. Several of the partners are listed above and include research organizations like IRENA and IEA, and programs like SC for All, and regional focus entities such as EcoWatts, the Center for Renewable Energy and Energy Efficiency. A marquee feature of the Solutions Center provides is a no-cost expert policy assistance known as Ask an Expert. The Ask an Expert service matches policymakers with more than 60 global selected experts as authoritative leader on specific clean energy finance and policy topics. For the example, in the area of wind technology, we are very pleased to have Ian Baring-Gould, Wind Technology Deployment Manager with the National Renewable Energy Laboratory, serving as one of our experts. If you have a need for policy assistance in wind technology or any other clean energy sector, we encourage you to use this valuable assistance. Again, it's provided free of charge. If you have a question for our experts, please submit it through our simple online form at cleanenergysolutions.org/expert, and you can also see the link on the slide. And we also invite you to spread the word about the service to those in your networks and organizations. Now I'd like to provide a brief introduction for our great panel that we have gathered today. First up is Oliver James Knight, who is a Senior Energy Specialist with the Energy Sector Management Assistance Program, or SNAP, at World Bank Group. Following Oliver, we'll hear from Idis Bowens. who is the co-founder and managing partner at Nazca Maps. Then we'll hear from Soren Kron, a wind power consultant for the World Bank and SMAP, supporting the Global Wind Atlas. Following Soren, we'll hear from Gil Lizcano, who is the R&D director with Vortex. Then we'll hear from Brian Orbach Hansen, who is the senior development engineer for the Department of Wind Energy at the Technical University of Denmark. And then our final speaker today is Neil Davis, who is the technical lead for wind resource assessment applications in the resource assessment modeling section for the Department of Wind Energy at the Technical University of Denmark. And with that brief introduction to our amazing panel we have today, I'd like to welcome Oliver to the webinar.
Hi there. Okay. So, welcome to the webinar, and thanks for joining us today. I'm Oliver Knight, and I'm from the World Bank, on the World Bank side, but in a unit called SMAP, which is a multi-donor trust fund operated within the World Bank and supported by around 12 bilateral donors. Just going to briefly go through some of the context to the Global Wind Atlas and how it came about in its current form. I've put up here that it's essentially a public-private partnership of sorts, in that we have the World Bank and DTU kind of more on the public side, but we're also collaborating and using privately provided data. So this goes back to 2017. DTU already had a Global Wind Atlas website in the public domain. But we were keen, we just launched the Global Solar Atlas, and we were keen to work with DTU to improve and relaunch the Global Wind Atlas and bring them into the same kind of usability and also update the data. So we've taken funding from SMAP and on behalf of our donors, and we issued from the World Bank a contract to Vortex, who is a private provider of wind data and other renewable energy data, and Vortex essentially carry out the mesoscale modeling, which is, they'll tell you more about, but is essentially the hardcore computer modeling. That is then passed over to DTU, who then carry out the microscale modeling, and then DTU have a separate contract with Nazca Maps, who have redesigned a very nice website that we now have. And this is what we essentially operating today. So what is the Global Wind Atlas? It's primarily a website available at globalwindatlas.info. In fact, we launched version 2.3 yesterday, and you'll hear more about that. If you go to globalwindatlas.info, you'll get to this page, and you can do a lot right from the get-go, just by pointing your mouse and gathering data and doing various different tests. You can zoom in, etc. So we have on the website, we have web-based calculations. The Global Wind Atlas also has now has the ability, we have some pre-cooked maps like this global map, but also maps by region, and you can see a couple of them here, and also by country, and that's Pakistan and Vietnam. And a newish feature that we have launched recently is the ability to essentially generate a map for any country in the world, and so you can get that on the website. So poster maps, which we find are very popular with countries and with people who are essentially looking for materials for presentations or looking to do some basic analysis. What else is also there is we also have generalized wind climate files, so you can actually download some of the data, and just recently also GIS files. So a lot of the data behind it is now freely accessible, and we encourage people to use that. We have a very we're very pleased with the reception of the Global Wind Atlas. As you can see, it's been growing since the relaunch. So it was relaunched in November 2017 with this collaboration between World Bank Group and DTU. And since then, the numbers have been going upwards quite steadily. We're at around 7,500 users per month right now. And you can see here some of the statistics. And we really hope to grow that over the next year, ideally with your support. I just want to mention that Global Wind Atlas has a couple of sister sites. We have the Global Solar Atlas, which is run by the World Bank Group as a separate project, but very closely related. And this is a good place to go for solar data, and you can also get the country maps on that website. And that's the address is very similar, globalsolaratlas.info. And we also run another sister website where we called Energy Data. The World Bank and SMAP have actually been commissioning solar and wind measurement campaigns globally over the last few years. We've installed quite a lot of wind masts in various different countries and solar stations. In fact, you can see the locations of those on the Global Wind Atlas and the Global Solar Atlas. And the data for that we post into energydata.info. And you can see here an example of that. There's also a lot of other energy data available there. The World Bank publishes, we try to publish all of our energy-related working data on this website. And we have a few other applications that are also available from that website. And the address, very similar format, energydata.info. So thank you for your dissemination. We really rely on our partners and interested enthusiasts to spread the word. Please use the website, use the tools, give us feedback. We're still working on a new version that will be coming out in 2019. So there's still room for improvement, and we're very keen to get any feedback and comments that you may have. Thank you.
Great. Thank you so much, Oliver, for that introduction. Now I'd like to welcome Idis to the webinar.
Yes, hello everyone. I'm Idis Bouw, the managing partner at Nazca Maps, and we have been building on the interface of the Global Wind Atlas. And I will now take my time to shortly show you the main functions of the application that will help you to travel through it. So I'm going to do that using the help section, to which you also get access. So we start when clicking on the help section. You get some general information about the Global Wind Atlas, and also 2 links to the sister websites, which were also just mentioned by Oliver, the Global Solar Atlas and the energydata.info. So, but let's move to the next step. We have a very common, everyone knows this, I guess, a search location bar here, where you can simply add a place, and then the map brings you to that area. But what is special here is that when you enter the name of a country, this search bar can bring you directly to the wind profile of that country. So the map brings you to the specific selected country, and on the right, on the sidebar, you see the wind resource information of that country. So before talking about the wind resource information, let's have a look at the layer controls here on the top left of the map. So the layer controls can simply be selected by clicking on the name, which will toggle them on and off. And you will see that there are 2 main groups also located here. You have the wind energy layers, where you have 3 types of capacity factor layers. You have the explanatory layers, where you have different types of layer that explain on how the power density layer is created. You will see that for each layer there is a small info button appearing next to the layer name. So if you hover over this info button, you get more, let's say, basic information about this layer. All the layers shown here are fully covering our global layers, let's say, or fully covering the globe, with an acceptance here in the wind measurement stations. This is a point data layer, where if you hover over a point and you click on it, you get more information about a wind measurement station that is located in this area. Important here to mention as well is that for some layers, namely the power density and the wind speed, these layers are available at different heights. So if we, for example, select the power density layer here, and we go to the bottom right of the map, you can see the interactive height legend here. So we are now looking at power density at 100 meter, and by simply clicking on the interactive legend, the map adapts to the other heights. The heights are available at 50, 100, and 200 meter. Another nice feature is when we hover over the map, you will see that the value there's a small arrow appearing next to your layer legend here, which indicates the value you are looking at where your mouse is hovering. When we have a layer selected with a unit that is available in different standards, let's say, you can click on the unit, and this gives you access to a different unit system. So if you're used in working in another system, you can change that over here. Okay, so if we pick in our help section again and we move on, we see that here on the top right of the map, we have basic map controls. These are standard map controls that allow you to change the background of the layer, remove the labels, go to a maximum screen overview, go to the location where you are located yourself, go to the global map again, and zoom in and out. Okay. It is also, in a side note, it is also possible to, at the bottom of the map now again, it is also possible to hide the legend and show it back again. This is important when you're working on different types of devices. Here we are looking at the desktop or the laptop screen. There's also a design for mobile and tablet. So the application is also accessible on your mobile and your tablet. So moving on through the legend, through the help section, I'm sorry, we see here we discussed about the layer legend, and we move to the sidebar. The side panel is an important part of the application. Why is that? Well, there's on the one hand, of course, the wind resource information that is shown here, but it also gives access to specific functions like map printing and GIS file download. So in the side panel, we have two important sections. We have the customized areas and we have the country and region. So, and I'm going to start here with the customized areas. So there are three ways to access data for a specific area through the map. There's the point way, there's the rectangle, and there's the polygon way. Simply by selecting one of those and drawing on the map, you can draw the specific geometry that you are most interested in. So if we move back to the point here for a moment, you can simply select that, and you can keep on putting points on the map, and you get more information about that specific point, at least the area around it on your side panel. The area around it, what do I mean with that? Well, when you place a point on the map, you don't get the exact point value, you get the wind data for an area of 10 by 10 kilometers around this point. So when a point is selected, you see here that the power density plot, the wind roses with 3 types of wind rose information. More information about the content of this data will be given in the next talks. And the wind speed, these plot data are shown over here. And the data that is plotted over here can also be downloaded by clicking here, where you can select which data you are interested in and the format you want it to download in. There's also the possibility to download a GWC file, a WASP-lib file, by clicking on the button over here. So another important part of the customized area is that you can save your area in your local storage of your browser. So let's say we have this point now drawn on the map. I can click on the save icon and simply say webinar test, for example, save. And now it is saved in my browser. If I go to my saved areas, I can see that I can bring it back up through the menu over there. So if I'm using the same browser on another day, I can always go back to my saved areas. Next to the saving the area, you can also share a link to that specific customized areas with other. You can download GIS files. This is an important feature. So once you have a customized area drawn on the map or a country or region area selected, you can decide to download the original TIFF files for that area. Now the file that you will be downloading when clicking on this icon is the file that is selected, is the layer that is selected on the side panel here on the top, on the layer panel here on the top left. So in this case, we are looking at power density with the height of 100 meters. So if I download this one, I will get a TIFF file with the original power density values from my custom areas, together with the GeoJSON file that highlights has the boundaries of my area of interest. Now it's important to notice here that, especially for countries, these files can be quite large and can only be used in the correct environment. So you need to have background in working with GIS data, and you will need as well GIS software to further process and work with this data. Okay, so second part of the sidebar that we have here is the country and region section, where you can select predefined areas, let's say. So here on top, you have a drop-down list of global drop-down list of countries in the world. You can just start typing here, and the map select it, and the map will go to that specific area, and the wind resource area information for that area is then adapted and shown over here. Now, once you're in a country, you can also choose to select a region in that country. You can do that by clicking and selecting in the drop-down list, or simply by clicking on the map. Now, one feature that I haven't shown yet is the map printing. So if we are in a certain customized area or country and region, you can click on this icon here, and you see that the map adapts to that. So for the layer that we have selected and the area that we are looking at, the layer is then showing the information here over the map. You can print this information in a PDF map, but before doing this, you can decide to adapt some parameters. You can, for example, include a buffer area by selecting it here and sliding the buffer slider. And this is interesting, especially when you're looking at coastal areas, for example. You can also decide to rescale the color legend. So the legend that we're looking at now is between 25 and 1300 watts per square meters power density. If I say scale to the min and max values that fall within my area of interest, you will see that the map adapts, the legend adapts, and it's possible to see much more variation in your image than before. If we then say we want to print this as a PDF, you get a result like yes.
Katie,
yes.
I'm so very, very sorry to interrupt. We've got to start to move on to our other presenters. Can you wrap up in a minute or two?
Yes, I'm almost there. No problem.
Wonderful. Thank you so much.
No problem. So if you print a PDF, you get a result like this. This is calculated on the fly, so it needs 10 to 20 seconds, and it can then be saved on your hard drive. Now to end, we are at the end. I just want to highlight also in the navigation top bar, there's a lot of information in the background pages. You have datasets, frequently asked questions, etc. You have the downloads page where you basically have short links to the GIS file downloads and the map printing that I just mentioned. And of course, you have the contact form, very important. If you have specific questions or you have remarks that you want to share with the Global Wind Atlas team, don't hesitate to do so. So that was all for my part. We are there.
Wonderful. Thank you so much. Thank you so much. I really appreciate it. Now I'd like to welcome Jake Badger to the webinar. He is the head of the section for wind resource assessment at the Technical University of Denmark. Jake, welcome to the webinar. Thank you so much for joining us today. That looks
hello,
great, Jake.
Hello.
Yeah, hello.
Good. So, hello world. Good morning, good evening, and yes, good day to everyone. And I would like to tell you about the ability to use the Global Wind Atlas for investigating country wind resources. So, yeah, I've been introduced. Yes, I'm from DTU Wind Energy, and I would like to say thank you to Clean Energy Solutions Center for hosting this webinar and giving us a possibility to tell everyone about it. So I just need to get to the next slide. Yes, so all of this would not be possible without our team, and I would like to just acknowledge the team right now. So I have a number of colleagues at DG Wind Energy who've been working hard on all of the microscale modeling and liaising with our consultant World in a Box in Finland, who's been partnering with us on the microscale modeling system. And then, of course, Nazca Maps, who we've just seen from EDES, the work that they've done to create a really nice interface with the data and tools that are provided by the Global Wind Atlas. So thank you to them. Also to Vortex in Spain, who've been doing the mesoscale modeling and providing that to us. Gil will get a chance to talk about that part in a little later. And then, of course, the World Bank, because of the funding that's made this new Wind Atlas development possible. So we're very grateful for that. And also, not just the funding, but also a lot of great ideas and really good, fresh motivation to create new tools and data sets, and also to connect it to many other of the SMAP projects. So my next slide is a sort of schematic showing the modeling down chain, and we'll talk about that again a bit later. But the main thing I want to talk about is it's a downscaling from large-scale reanalysis data, and then we do this mesoscale modeling step, and that's under the responsibility of Vortex. And I've marked it out by this dashed box, and I'm going to be using this to signify the modeling influences later on. And then when the Vortex have done the mesoscale modeling, then that is passed to us, where we do generalization and microscale modeling. And I've shown that by this now dotted box to indicate the microscale modeling. And here we go from scales of around 3 or 9 kilometers down to our calculation every 250 meters around the world. We have a high resolution wind climate calculated. So if we take an example of what you can now do with the latest version of the Global Wind Atlas in Global Wind Atlas 2.3 is the latest version, we can create, as EDES explained, these country poster graphics. And I would like to say everything I'm showing, apart from a couple of figures, are actually screenshots out of the Global Wind Atlas, which can sort of demonstrate what you can do just by going onto the web browser. So here we have what has been generated by the Global Wind Atlas for the Philippines. And I thought that was an interesting example because it features some mesoscale influences, flow, and also some microscale flow features. And if we look at the poster map, we can see that there's some places with low winds below 3 meters per second, and some places with higher wind speeds up to around 10. And if you look at this figure we have on the right, it indicates that if we look at this graph, on the x-axis, it shows the percentage of windiest areas. So when that is 100%, this is actually saying what is the country average wind speed. And if we read it off this graph, it says it's 5.3 meters per second. But actually, wind is deployed in the favorable sites. So what we're interested in doing with this high-resolution Global Wind Atlas is looking at the best sites. And we can do that by gradually looking at a smaller and smaller area, saying we're only looking at the windiest areas. And that's what this graph is indicating. So with this graph, we can look at, for example, the 10% windiest area. We can see that we have a mean wind speed of around 8 meters per second, a bit higher than that. And so that's how we use this graph and using the high-resolution Global Wind Atlas data. And we can do this for customized areas and also countries and administrative regions. The next thing we can do is look at it from the point of view of power density. So it's the same kind of poster map produced again, and then on the right-hand side you can see the power density graph showing the percentage of windiest areas, and then the increasing in the power density mean as we look at the windier areas. So here you can see the country mean power density is around 220 watts per meter squared. But if we go to the windiest areas, at 10% windiest areas, we see it's around 700 watts per meter squared. So this is like the whole essence of why we did the Global Wind Atlas, was to make sure that the windiest areas are emerging in our assessment of wind resources. So I want to now explain a little bit about, if we're looking at a country, what kind of features can we examine and investigate? So here we are, we're going to zoom in on a part of the Philippines, the Calamanian Islands and the Guimaras Strait. And the reason I do that is because if I can highlight it with my this sort of red pointer, I hope you can see that. We've got this dashed ellipse. We've got 2 dashed ellipses which represent 2 mesoscale features that are caused by a kind of gap flow that's occurring in the straits between these main islands of the Philippines. And if you look on the right-hand side, we've got the elevation map, which is from the Global Wind Atlas again, and you can see these gaps, these straits between the islands where there's elevation going up to around 1,500 meters. So it's really interesting to be able to sort of browse the world and pick up these interesting mesoscale features that are enhancing wind resources. If we look at the next slide, we're zooming in much deeper now into the Guaramas island. And again, I've put in the dashed lines, which showing the mesoscale feature of this gap flow through the strait. And if you look on the right now, you can see the windrows that is being created by this point customized area that's been put down on the island. And you can see that the winds are predominantly coming from the northeastern sector, which is consistent with this gap flow concept. And this is where the main winds are coming from. But if we look at the island, we can see now a lot of variation of the wind resource. And this is the wind speed plotted. We see a lot of variation. And now we need to kind of examine why is that happening. So we can look using the Global Wind Atlas at the elevation map and also the roughness map. And the elevation, we can see it's not super high. It's not like the elevation on the main islands to the west and to the east, but we are seeing variations of a few hundred meters on that island of Guaramas. And also, if we look at the roughness map, we see variation of around 5 centimeters to around 1.5 meters. And this is also representing cultivated land and also some forest areas and also some city city areas. So we see variation in elevation, we see variation in roughness. And now we go back to the wind speed map for the island, we can see different features that are caused by this. These are now microscale features that are being picked up and showing where the strongest resources are. If we look at the west coast of the Guaramas Island, we can see some good, so I just highlight that with my cursor. Here we can see some strong resources. This is a combination of the low roughness because of the seashore and also headlands where there's some orographic speed up effects as the flow has to go over the terrain. So this is just a sort of way of interpreting the different kind of influences of mesoscale and microscale that you can do with the Global Wind Atlas. Another thing you can do with the Global Wind Atlas, as you know, you can have different maps, a sort of underlay. And I think this is very nice because, for example, the road map, you can get an idea of the human geography surrounding your site of interest, not just the meteorology, but here, for example, you can see that there's quite a large city nearby the island and nearby the strait. And you can also look it up and kind of get a context for the kind of place you're examining. For example, the city there has 500,000 people. You can also look at the satellite imagery, which can give you a check of the land cover. Also wind features. If it's a desert, for example, you can sometimes see sand being blown features, which can then confirm what is the Global Wind Atlas is saying. Here we see cloud streets, which also is confirmation of a northeasterly wind at this time. You can also put capacity factor data. Now is a new feature that's very nice, that you can actually get a feeling for if I had a turbine placed in the terrain, what would be, get an idea of the production. So here you can choose between 3 different IC class turbines. And this is a nice new feature which goes beyond just showing sort of meteorological information. What I always like to do with this feature is to add the Ruggedness Index, which gives an indication of the complexity of the terrain. In steep terrain, we know that our linearized flow models are kind of more limited. So the recommendation is that if you're in an area with a rather high ruggedness index, this means it's important to go towards some more modeling, possibly using CFD modeling, and also go towards more measurements on site. But where you see the low ruggedness index, or where it isn't masked out, we can be quite confident about the results that are being shown by the Global Wind Atlas. And this leads on to validation. So we have done an in-house Global Wind Atlas 2 validation using 60 wind measurement stations in 7 countries. And the sort of summary of those results are, if you can see the graph here with the global wind atlas derived wind speed plotted against observed wind speed, that we're seeing a mean bias around -3% and a mean absolute error of 9%. And this is work that is very important to continue and to disseminate into the global wind atlas. And that's why we're very happy to have the sort of integration of the data from the SMAP country wind mapping projects and connecting it to the energy data info webpage. So here on the global wind atlas, you can see the location of the measurement sites, and these will be integrated into our validation. And it's important to remember the validation principle is that these data from these very high quality measurement sites are independent measurement data, and then they are compared against our global wind atlas model data. So it means that that they're not mixed up. It's not a matter of calibrating the global wind atlas data to fit the independent measurement data. No, they're totally independent. So you have global wind atlas model data anywhere in the world, but the best thing of all is to be able to see that you have global wind atlas data and a validation with measurement data, and that's what we'll be able to provide in future versions. And it's important here to mention our partners there, which are involved in the SMAP country mapping projects. And that's DNVGL with their in-country partners and 3E with their in-country partners too. And so in summary, I'd just like to make the go-home messages, which is with the Global Wind Atlas, you can understand physical phenomena that give rise to wind resources. And these can be thought of in terms of mesoscale effects, microscale effects, and you can investigate wind speed distributions and wind roses. You can also quantify the resource with wind power density and now with capacity factors. And you can estimate the level of uncertainty using the Ruggedness Index mask. And in the future, with our next steps with validations, they'll be built into our website. So you'll be actually able to get some kind of feedback for the validation work within the web layers. So that's it. Thank you very much for your attention.
Great, thank you so much, Jake. Now we'd like to welcome Surin to the webinar. Surin, welcome to the webinar. Perfect. Your screen looks great, Surin. Thank you so much.
Sorry, I was muted. So,
no worries.
Okay. So anyway, one of the best new features of the Global Wind Atlas, in my view, is the fact that we can display capacity factor maps to see where the wind resources are. So this presentation is about the data you can download from the Global Wind Atlas, and it's very much oriented towards practical use, towards wind farms, and it's primarily for people who would want to download the data to their own GIS system. Now, as my example, I'm primarily using Uzbekistan because a few years ago, I wrote the terms of reference for a mesoscale and microscale study in Uzbekistan in order to find the wind resources. Now, I wouldn't do that today, and the reason is that we have the Global Wind Atlas, and the Global Wind Atlas actually, to my mind, actually gives us a very clear indications of where we find the good wind resources. Now, what I've done here is I went on to the Global Wind Atlas, and I did the color focusing that IDES was talking about. So I said here, well, I'm really interested in stuff that's between 35 and 45% capacity factor for a class 1 turbine. And I get these, you can see about 5 patches roughly in the country that look interesting. Now, this is what it looks like on my own system. And again, I do the color focusing on my own system and I get the same picture. Now, then I overlay it with a grid map. Now, this is not a feature we have in the Global Wind Atlas yet, but it's coming. But I know how difficult it is to get hold of this data because many countries consider it an important security issue, and it's very hard to have it properly updated. But we're lucky enough that we have the grid in Uzbekistan, and as you can see, a lot of the connections actually run through the neighboring countries, and you have connections to the former Soviet Union, which really is part of the whole grid. So the interesting wind resources, as we can see them here, the ones which are to the northwest, well, we can't really reach them because there is no grid there, but we have these 4 to 5 patches which are interesting. And then I add on the future grid, I mean the planned grid extensions, and we get an idea that we might even be able to tap the resource up to the far northwest. Now, what I'm interested in seeing now is what actually happened. What did the consultants really choose when they picked the 2 wind sites where they wanted to do measurements? And of course, they picked 2 of the spots we have, which happen to be near the grid. Now, one of these spots is called Nukus. It's near the town of Nukus. It's out in the middle of the desert, as you can see. This is from Google Earth. And the Met mast, I could actually find it on the map by seeing its shadow, but it's out there in the middle of the desert, and we have kind of a ridge to the left that looks a little bit interesting, I think. The consultants, before they did this, actually did the mesoscale modeling using a model called FITNA, and they said that, well, we think at 85 meters we'll have 7.3 meters per second, and when they measured for a year and corrected it to a long-term mean year, they got 7.6 meters per second. And of course, I'm curious now to see what does the Global Wind Atlas say. Well, when I look it up, we actually hit the 7.6 meters per second, but this was done for 100 meters and not really done for 85 meters. And this is where my own program comes into play, because I can then adjust to 85 meters to see what happens there, and there we get 7.45 meters per second, just about, which is right in the middle of what the consultants estimated originally and what they actually measured on the site. Now, how do we do this? And this may look a little bit shocking to some people, and if you're not into statistics and math, you might relax for a while. But basically, the way we can do this is that we can first of all look at the graph to the upper left, which shows the 3 points where the Global Wind Atlas has a wind speed estimate. And then I assume that we have logarithmic wind shear, and that's how I estimate the blue and the red curve. And the gray curve is just there to show what happened if we estimated all the way between 50 and 200 meters. The next curve shows the wind power density from the Global Wind Atlas. And when we have those 2 figures, and if we assume that we can represent the wind speed distribution with a Weibull distribution, we can actually find in the graph to the extreme right, we can find the Weibull K factor by height. And once we have that, in this case, you can see that it actually keeps dropping with height. This is typical for offshore areas, or like here, desert areas with super low roughness. If we use that curve plus the wind shear from the curve to the extreme left, well, then we can actually work our way backwards and get the Weibull A distribution factor. And then in the graphs on the lower part, I have indicated the wind speed distribution for the height we're looking at right now, which is 85 meters. I can change that. I have a power curve for the wind turbine, which I've selected here. And I then adjust it for the local air density, which is a layer you can also download from the Global Wind Atlas. And then I can get the next graph, I mean number 2 at the bottom, which actually shows me what is the capacity factor by height in this spot. And in this case, with this particular turbine, there are 2 available hub heights, which I have indicated there. And the final graph at the bottom at the left is a graph that shows you the power density distribution and how much of the power density is actually converted into electricity. Now, again, to satisfy our curiosity, if you just hover over an area on the Global Wind Atlas, in this case it's on my system, you will find that we have a capacity factor roughly around 40% on this side, a gross capacity factor. And if I adjust that, And I actually here took the turbine layout that was done by the consultants, and they too actually thought that the ridge was interesting, which Global Wind Atlas think too. Then we get an average gross capacity factor of 42% in this case. But if we adjust that, and this is what I can do with the program, as I told you, we go to a lower hub height of 94 meters, and instead of having a rotor diameter of 112 meters, we have one of 101 meters. Well, then we actually hit a capacity factor of 39%, which is extremely close to what the consultants estimated in the first place. So this is actually, of course, a success, but don't expect that everywhere. This is the other site in Uzbekistan where I did the same calculation. We're off about 3% with the same turbine, same hub heights, etc. But still, it's pretty impressive, and we're pretty close. Now, I'll take one more example. This is from Morocco. This is a fantastic site. It's called Koudia El Baida. It's located on a ridge, a 200-meter tall ridge, right next to the Strait of Gibraltar, next to Tangiers. And again, here you can hover with your mouse over the spot, and what you find is a capacity factor of around, gross capacity factor of around 50%. And actually, this wind farm has been operating, I think, for 18 years with Vestas turbines. Wait a minute, I have the graphic. No, I will just go back. With Vestas V44 turbines, and it actually has the capacity factor of 47%. So we're very close in our estimate, but here is one of the dangers of the system. You have to be very careful, because on places like this where you have steep terrain and where it's not completely flat, then you'll find that if you move from one pixel to the next and look at the graph in the upper left corner, this graph looks fine. And the next one actually shows that we have inverse wind shear, which is probably perfectly true, but it means that you can't rely on the resolution of the Global Wind Atlas. You need to do actual microscale modeling in order to make this work. So the let me just see here. This is another example. This is Bangladesh. We measured with a LiDAR. We measured about 5.2 meters per second at 107 meters. The Global Wind Atlas is a bit off, with 5.5 meters per second, but still we're within the margin of uncertainty. And then I decided to pick an offshore wind farm in Denmark. This is a large offshore wind farm that's been operating for 7 years. We get something which is extremely close to the real figure. And just to finish off, this is kind of for fun. I took all the 57,636 turbines in the United States, and if all of those turbines were the ones we used in our example in the Global Wind Atlas, and we would have a capacity factor of 33% in the United States. But what's interesting about this is that you can actually go onto the map and you can actually study how the developers placed their turbines, and you can see that the Global Wind Atlas is pretty much in line with what the developers do. So to conclude, I think the Global Wind Atlas is a great, if not fantastic, tool for finding windy sites. And particularly if you use the color focusing feature on the maps, you have a great chance of doing it. It's often very accurate, even for local wind resource details like wind shear, reverse wind shear, and what we call Bible K reversal. But it's not a substitute for microscale modeling. So don't rely on the Global Wind Atlas for siting your wind farm, but do rely on it for finding good spots. Thank you very much.
Wonderful. Thank you so much for that. And, you know, we're going to pause here and take a few questions from the audience. From our attendees, please feel free to submit a question at any time using the question pane. I would like to begin with a question for Oliver. For the wind GIS file or data, is it freely available for the attendees or others registered participants to use and do analysis for their very own countries?
Yeah, so I mean, essentially everything on the website is free. So in that sense, it's all freely available, and the GIS layers were just added with version 2.3. So so that's a new feature. But all the maps, GIS layers, and anything else you can get from the website is entirely free, and there's no need to register because we actually don't have a registration system on that website on purpose. And all the saving features you saw that IDIS demonstrate, they're all saved on your local machine. So there's no communicating back to the server with that.
Great, thank you so much. Our next question is for IDIS. IDIS, this participant says for Zambia measurements, how many years is the data available?
I think we should pass this question more to Jake or Søren, maybe.
Yes, this is Søren. Yeah, this is Søren. We have been measuring in Zambia for almost 24 months now. Actually, in 1 month, we will have 24 months worth of data. And that's quite interesting. And one of the things I can tell about Zambia is that there is a better wind resource than we thought. Only you have to go very high up because there's extremely high roughness. So you should move to at least 130 meters hub height in order to get some real wind resource down there.
Great, thank you so much. Back to IDIS. A question is, when placing a point on the map, aerial statistics are provided in the sidebar. How is that calculated?
Well, the data that comes in, we receive through the API of DTU. So the actual calculation of the data, again, I should pass the word to, this time, I think, Neil.
Yes. So the data that's taken, so basically we get the point, so we get the region, and then we clip that area out of the raw data from our microscale modeling, and then we end up calculating just the gross statistics that get sent back to be displayed on the website. So like for the averaging fields like Jake was showing, it's just a simple average over kind of each percentile as you would expect.
Great, thank you so much, Brian. Our next question is for, who's our next question for? Is for Jake. Jake, it says, does the downscaling from meso to micro scale flow always produce high revolution modeled turbulence? And what is the uncertainty of the modeled turbulence? Is it recommended for use in turbine stability studies?
Okay, so that's a very good question, and it's not something we address in the Global Wind Atlas at all, actually. So these are all wind climate statistics for the purpose of doing a production estimate. So it's a wind resource as in the production, annual energy production of a turbine, putting it through a turbine power curve. But it is something we are interested in pursuing. Actually, we have a project starting next year called the Global Atlas of Sighting Parameters, and it will address exactly this. So it's a project with Danish funding, and we have a partner, EMD, in Denmark. And what we'll do is try to create the meteorological data that's required for IEC turbine class typing. So for that, we'll need to know things like the extreme winds, the turbulence intensity, inclination angle, these sort of things. So it's not something available yet. But it's something we're moving on to in a project that is very much related to the Global Wind Atlas.
Great, thank you, Jake. And to follow that up for maybe you or Søren, can the GWA data be improved with measurement data?
Okay, I could try. Yeah.
Go ahead. No, go ahead, Jake.
Okay, so my take on this one is that we actually try to keep these things separate as possible. So we do it as a validation. I mean, you can find out whether the Global Wind Atlas is reliable against a good quality measurement. So if you have a site measurement very close to where you're thinking of your wind farm development, then go for the very high quality wind measurements. That's not substituted by the Global Wind Atlas. But we're not interested so much in sort of making a calibration of the Global Wind Atlas by sort of adjusting it to a measurement. So, Søren, do you want to follow on that?
Yes, I can say that. We think the validation program is very important. We are operating about, I think, about 60 80-meter masts around different countries, and we have 3 LiDARs up and running. And we think it's important for developers to know the uncertainty of what we're doing. And that is why it's important not to recalibrate the data we have in the Global Wind Atlas, but it's much more important that we know how certain or uncertain is the data. And that's where local measurement data actually helps us. And to the extent that there are countries that have very high quality measurement data, the World Bank is actually interested in getting hold of that data so that we can do even further validation of the Global Wind Atlas. That's how we did it in Vietnam, where the German Development Agency had already done wind measurements. Thank you.
Great, thank you so much, Søren. Our final question for this little segment of questions is for IDIS. Is it possible to access to the data directly via an API or only via the website?
Well, it is possible to access the data through the website. There is the possibility to download some data, as was shown during the demonstration, but there is no direct link through an API for the data. No.
Okay, just to clarify, we had a little bit of audio issues with your audio, so it's not possible. It is possible?
No, it's at this point it's not possible to access the data on the Global Wind Atlas through the API, through an API. So the only way to access the data at this point is by looking at it and downloading the plot data or the GIS files through the interface.
Thank you so much for clarifying that.
Okay.
Wonderful. Great. Well, we're going to break from the question and answers. We're getting some great questions from the attendees. Again, you can ask a question at any time using the question pane. And if we're not able, we've had so many questions, if we're not able to get to the questions today, we will follow up with the attendees after the presentation. I would like to now welcome Gil to the webinar for his presentation.
Hello. This is, so this is Gil Scano from Vortex, and I'm gonna give you an overview of what we are doing now to provide a new meso layer for what will be the next version of the Global Wind Atlas. So I'm working at Vortex, which is a company that our specialization is to provide a wind resource based on weather model. We use a WRF model as our core engine, and we provide what our target is to provide the highest quality resource information for any place in the world. We focus on demand simulation, so the simulation that requires quite a lot of computing capacity. So our target is to provide this access to the end users, and we relied on the reanalysis as the global input to drive the simulation. And as I say, we plugged on the reanalysis and atmospheric modeling technology. So for the Global Wind Atlas, we've been producing a transition layer between the reanalysis and the microscale. So what we have done is to enhance the reanalysis with the missing element, that is the mesoscale and the synoptical flow adjustment. So we use the model WRF, that is a weather model. It's like the model that we employ for the weather prediction, for instance, but we run this model retrospectively, so back in time, so using the global reanalysis as input data, and then we produce for a global layer of wind speed, direction, and other variables, that all together allow us to generate the generalized wind climatologies. That is what we handle to the TU and to work in a box to proceed for the downstreaming with WASP. So as Jake showed before, this is like this is the scheme, the diagram of the methodology. We have on top the reanalysis that give us the best approach to the atmospheric conditions over the last 30 years, and then we enhance the reanalysis with the mesoscale modeling and providing the necessary information for the microscale chain synchronized. So in the version 2, that is the one that you have alive, we employed era interine and a mesoscale resolution of 9 kilometers. So we run the model WRF globally with 9 kilometers driven by the reanalysis era interine. Now what we are doing now is updating this meso layer for what is going to be the new version of the global wind atlas. We changed the driver, so we use now era 5, that is the latest generation of reanalysis, and we increase the resolution of the mesoscale layer up to 3 kilometers. So at the end, we are getting a pixelized wind resource information of the globe with 3 kilometer resolution. So just to give you a brief idea of what is changing, where we're changing the resolution of the driver of the reanalysis. Era 5 has up to 30 kilometers of resolution, a much more vertical level that is very important for the mesoscale model quality, capturing the quality of the mesoscale model performance. And then we improve the meso layer with a resolution of 3 kilometers, and we extend the offshore domain up to 3 kilometers. And then we provide all the microscale information, and also we are generating 2412 tables that give you an average values of the daily cycles for every site. So as for the version 2, what we had done is to divide the world in tiles. Specifically, we produced 2,460 tiles, each tile with 3 kilometer resolutions. The size of the tiles depends on the regions, but the minimum size is 3 by 3 degrees, and we have a buffer around to avoid any noise on the border of the modeling. So we are going to finish this new run of this new meso layer by mid-January of 2019, and this is where we are now in the production. We have already simulated most of the world. We are just missing part of China and North Siberia and some regions in Alaska, but the rest of the world has already been done, so we are on time to finalize the simulation. And this is along with the mesoscale modeling, as I say, we generate the generalized wind climatologies. That is the main input for the WASP downscaling. So next year, all this will be there in the new version of the Global Wind Atlas. Thank you.
Great, thank you so much for that. Wonderful. And we'll now move to Brian for his presentation. Brian, it seems that we're having some trouble. We will try to change the presenter to you again. Oh, it looks like we were able to.
Yes.
Oh, great. Thank you so much.
Yes. So yes, this is actually Neil presenting. Yeah, I'm going to be presenting also about the Global Wind Atlas version 3, but I'm going to talk now about the microscale modeling improvements, and I'm going to give a little bit of an overview of the microscale modeling and how we've kind of done that. So again, this chart that everybody has seen a number of times. So when we're talking the microscale, we're talking about this piece the generalization that Jill just talked about a little bit, where we kind of couple in between the mesoscale and the microscale, and then the microscale modeling itself. So at DTU Wind Energy, we have developed this microscale methodology that we've used for quite a long time. It actually was developed during the European Wind Atlas in 1989. And the idea here is that we can use a two-step process in order to predict the wind at a fine resolution at a local place. So we'll start with something like the mesoscale wind climate, which gives us a relatively coarse idea of that. And then we can remove some of the effects of that. I'll describe this on the next slide in more detail. And that gives us something that we call a generalized wind. So this is a wind that doesn't have the mesoscale topography involved in it. And then we can take a high resolution topography and we can apply that and we can get the predicted wind climate. So now I'll talk about those steps in a bit more detail. So when we talk about the generalization, the reason that we have to do this is because the mesoscale model has a coarser representation of the surface features than what we know is happening in reality. So we can see here on this image of the topography that the yellow line would be kind of how we might see this terrain inside of a mesoscale model, while in the microscale model we'd be able to see all of these smaller hills and all of these individual speed ups and things like that. But we don't want to double count the terrain that we had already from the mesoscale model, so we need to remove that. And so that's the process that we work on in generalization. Then the other thing that we look at is the roughness characteristics, as Jake mentioned. And one of the biggest roughness characteristics that we care about is the coastline. And here you can maybe see that there's green tiles and there's blue tiles. The blue tiles are what are water inside of a mesoscale simulation, and the green are the land. And you can see that these don't necessarily match up with the coastline of Denmark in this image, where we have a coastline where maybe a quarter or more of this box is looked at as being over land, but it's actually all represented as water inside of the mesoscale. So we have to remove kind of those limited representations of the topography. So that way we can do the microscale modeling and we can add those in. So when we are interested in these two features, the reason that we're interested in these two features for wind is that when we have flow that's going over a hill, as shown in this image on the left, we get a compaction or a compression of the streamlines as we go over the flow or over a hill. And that means that the flow is actually speeding up over the top of the hill. So we end up with faster winds on the hilltop than what we have on either side of the hill. And that's one of the reasons that we want to take this high resolution orography into account. When we look at the roughness features, here we might have an upwind roughness that's really smooth like the water. And then when we go over land, we have a more rough surface. And that means that we also have slower winds. However, that transition is not an abrupt transition. So we actually model in a roughness change model this transition layer that happens inside of this. So given that kind of background in the microscale modeling, what are the improvements that we're looking at in the Global Wind Atlas version 3? So first of all, as Jill mentioned just before, we're going to have updated mesoscale data, and that will be a big improvement in our microscale modeling as well. Then we also are improving the terrain data set that we have. We're doing some behind-the-scenes processing of that. Then we're actually using an entirely new roughness data set that's a much improved ACES CCI land cover data set as opposed to the globe cover data set that we had used previously. One of the really nice things about this also is that the CCI land cover is a much more recent land cover data set, so therefore it better represents the land as it is today. And then in the microscale modeling side of things, we're going to be moving to the latest version of WASP. So we have a number of improvements over the version that has been used before, and all of those will now be brought into the Global Wind Atlas. There's also been some performance improvements, and then we're working on running everything in a lat lawn space instead of running it inside of the UTM space that has previously been done. And this will mean that we'll have better analysis and better visualizations that we'll bring to you on the website itself. And that flows into this slide about the new features of the website. So we're going to be adding a number of new map layers. At the fine microscale resolution, we're going to be providing you with an air density map at 100 meters. And then we're going to be using the mesoscale data that's being provided to us to provide more information about the temporal nature of the wind. So we'll give you a diurnal wind pattern map, and we'll give you some interannual wind speed maps, both of wind speed and of power density. We're also going to be providing new charts on the sidebar of this monthly diurnal time series table, which was this 2412 table that Jill mentioned. And we're going to show you a time series of the 10-year interannual wind speed so that you have a better idea of how the wind varies in time. And then finally, as has been mentioned before, we're going to be doing some enhanced validation. We're going to be adding in approximately 28 sites from Pakistan, Vietnam, and Zambia, as well as other SMAP sites. And then we'll be comparing those for both the generalized and the predicted wind climates. And our evaluation, or our validation results, will also help us determine what areas we should use to drive the future measurement campaigns. So that's all that I have. Thank you.
Great. Thank you so much, Neil, for that great presentation. And thank you to all of our panelists for all the outstanding presentations. As we shift to the question and answer session, I just want to remind our attendees that please submit your questions using the question pane at any time. We also keep several links up on the screen throughout for a quick reference that point to where you'll find information on other upcoming webinars and how to take advantage of our Ask an Expert program. We've had some great questions from the audience that we'll use the remaining time to answer and discuss now that we're finished with all the presentations. I'll do my best to address it to the appropriate panelists, but please feel free for anyone to jump in and also answer the question. I will begin with Jill. Are you using the same WRF setup in all the regions of the world?
Yes, we are using the same version of WRF to preserve the consistency of the model across the simulation.
Okay, great. Thank you so much. Our next question is for Soren. Soren, how long, months or years, will it take to make field measurement on wind spot area before installing wind turbine for power generation?
In most cases, we would recommend 2 years, I think, but you do see projects which are done solely on the basis of 1 year measurements. It depends a lot on how good reference data you have in order to convert your time series into something that represents a long-term wind climate. But I would say 1 to 2 years is normally what is required in order to build a wind farm.
Okay, great, thank you. My next question is for Jake or maybe Neil. Can the GWA also help the user to visualize the flow, turning, or veering enforced by complex terrain or roughness features?
Yes, I could try to take that. Hello, Jake here. So yeah, you can look at windrows at different heights. But I would say in complex areas, then remember that the flow model isn't going to give you such a trustworthy result, say, compared to what you might get from a CFD, a computer fluid dynamics code. So it's kind of yes, but with caution.
Okay, great. And to kind of follow that on,
oh, can I just say one other? Sorry, could I just say one other thing? I forgot. One important thing to say is that you don't actually, in the Global Wind Atlas, you can't get so much detail down to a point because we allow the tools to work on the minimum size is a 10 by 10 kilometer area. So you won't be able to examine a point in the same way as what perhaps the questioner is wanting to do. So in that case, I think you really need to be able to do the modeling by yourself if you want to get down to that level of detail.
Great, thank you so much. And just to follow on with that, kind of a two-part question, how reliable is the data in the GWA And also, is the GWA in general underestimate or overestimate in the wind resource?
Okay, so I can take that again. I showed in the Global Wind Atlas 2, we did this validation with 60 sites. And this is the validation as we see it should be done, where you actually have information at the measurement site, and you need to account for the measurement site characteristics. So if it's on a hill or what kind of roughness situation it is in. And these can be then compared to what the Global Wind Atlas is giving you. And we see I think it was a mean absolute error of around 10% and a bias of -3%. So it's slightly conservative, but only slightly. But what we want to be able to do more is actually say that we can make a prediction for the uncertainty given the site. So if we're looking at a site which has very low ruggedness, so it's very, very flat, it has a very simple roughness, we would expect the uncertainty to be lower than that, maybe within 1 or 2%. And if we're in a place where there's roughness complexity, but very flat still, then we might say it's around 5%. And if we're in a place which is complex terrain, simple roughness, then we may be looking at 10 to 15 to 20%, depending on the complexity. So I think we can do what we're working towards in research projects is to be able to make predictions of the uncertainty given the site characteristics. And that's something we can build on with all of the validation we're doing together with the SMAP projects too.
Great, thank you so much. And we keep having great questions come in, so I appreciate our attendees for asking so many great questions. Soren, what are some of the wind measurement instruments that you have used out in the field of the wind area to measure wind speed and wind availability?
On the approximately, as I said, 50 or 60 masts, we have only first-class instrumentation. So we have absolutely, you could say, top scientific grade instrumentation and MASNet calibrated instruments. So these measurements are sort of textbook-like, the best you can. And then we do have we have 4 LiDARs right now operating in some places. And I would say, by the way, that LiDAR is much easier to deal with. I mean, planning permission has been hell in many of these countries. But it's top-notch equipment, and we measure at multiple heights up to 80 meters. And in the case of LiDAR, we measure up to about 200 or 300 meters, depending on the instrument we're using.
Great, thank you so much. Our next question, I believe, will be for Neil. Neil, what is the minimum and maximum mesoscale measurement efficiency, and what are the minimum average wind resources needed to be viable?
I'm not quite sure that that I fully understand the question. Can you run that by one more time?
Yeah, absolutely. What is the minimum and the attendee wanted to know, what is the minimum and maximum mesoscale measurement efficiency, and what are the minimum average wind resources needed to be viable?
Sure. So I guess by the mesoscale efficiency, I guess that they're asking how coarse of a mesoscale could we use in order to refine down to the microscale, and so if I'm assuming that that's correct, then I would say that it really depends on on the scale of the mesoscale features that are impacting the region of interest. So of course, when we're looking at something that's global, we kind of want as fine of a mesoscale as we can get, so that way we can capture these features like the gap flows that Jake showed in his presentation, as well as things like sea breezes and other mesoscale effects that are important to capture. However, I would also say that our very first Global Wind Atlas, we actually used some reanalysis data that was quite coarse. It was at about 50-kilometer resolution, and that at least gave us kind of a starting point. But I would say, as is often the case with mesoscale modeling, that you should look for, as good of resolution as you can afford, I guess. And then the second question, I'm not quite sure that I have an answer to.
I can pick that up. This is Soren. I would say that it really, I mean, the economically viable wind speed really depends on the country. If you're up against diesel, say you are in the middle of the Maldives, well, it's perfectly fine, even if your electricity will cost you 25 US cents per kilowatt hour, because diesel is twice as expensive. So there, 5.5 meters per second is fine. If you go to a developed country like Canada or the US, you have to be competitive with other sources of local power generation. And there you might want 7 meters per second. But it's very hard to give a general answer, because it also, a lot depends on the wind distribution, and a lot depends on the air density. So there's not a simple answer to that question.
Great. Thank you so much, Neil and Soren, for answering that. And back to Neil, how well does the GWA data perform at micrositing?
I guess that we would again kind of lean back towards a little bit of Jake's analysis, but I would say that our general, the general way that we point at the way to use the Global Wind Atlas is to not use it for micrositing. There are a number of assumptions, kind of as Jill mentioned, about using a common WRF setup to be consistent. We do similarly for our topography and for our roughness layers, where we make choices to try to be consistent across the entire globe that may or may not be the most representative for a very specific site as you need for micrositing. So our general point of reference, and also as Soren kind of talked about in his presentation, is if you are very worried about micrositing, you should you should do your own custom microscale modeling with your own topography and roughness maps that are taken from on-site observations.
Great, thank you so much. Oliver, for a question for you is, how does the GWA compare to commercial wind data or wind development software?
So we've purposely, I mean, with both the Global Solar Atlas and the Global Wind Atlas, we're very much trying to bridge the gap between having basic understanding of resource, but also not treading on the toes of commercial providers. And I think with the Global Wind Atlas, that's very clear, because if you're developing a wind farm, you're going to need to go to a level of detail beyond what the Global Wind Atlas can provide, and you're going to need to do analysis that is much more detailed, and you're also going to need ground measurements. But what we're trying to do with these resources, and specifically with the Global Wind Atlas, is provide a better starting point both for governments and developers, so that everybody's on the same page, so that there's one single data set that covers all countries, that can be compared between countries and within countries, so that everybody essentially has access to some good quality data to do planning and to do initial site scoping. So that's very much the position we're trying to take. The Global Wind Atlas doesn't take you to that next level of fully developing a commercial wind farm, and it's not intended to do that.
Thank you
can
for
I
that.
add?
Oh, please, Jake, go ahead.
Yeah. Yes, Jake, I just wanted to follow up what Oliver said. So I agree completely with that. I think we can use the Global Wind Atlas as a guide to what should be the next steps in the country. Should it be a measurement campaign? Where should the measurements be placed? Or is this country requiring some other modeling effort, perhaps where we know that there's some mesoscale features that need some extra custom mesoscale modeling, or maybe it's complex terrain, so we say that we need to do something custom for the microscale modeling. So I think we can use the Global Wind Atlas in a way to steer what should the next steps be, and do that in an efficient way, well, effective, because you can actually then skip out the parts that are already sort of you can avoid making mistakes, and use this as a guidance for more rapid deployment of wind in countries where that's relevant. And that's what the Global Wind Atlas can point to. Great,
thank you. A question just came in, is where are the visualized were the visualized turbines and the grid systems input outside of the Wind Atlas online map?
Yes, they were. And as I was saying, the option of showing the grid map is something that will be coming to the Global Wind Atlas, but it's quite some work to get that done. But everything I presented in my show was done on my own computer and with my own system using the data downloaded from the Global Wind Atlas.
Great, thank you so much, Soren. Our next question is for Jill. Jill mentioned this attendee referenced your presentation that mesodata period is 30 years. Does GWA allow the user to change the reference period, like to 10 or 15 years, and check the modeling outcome?
No, that's not possible because we need to fix this period for the meso layer production. So we are producing the time series of the mesoscale simulation for the last 10 years. That is the period available now, based on ERA 5. So it's covering 2008 to 2017.
Okay, great. And then keeping you on the line, what do you expect? What improvements do you expect in version 3?
Well, it's clear that we expect the model to improve the regions where the version 2.0 still is not as good as we want, and because we have already looked at some outputs and some internal validation, and also because the improvements in the ERA 5 as well, we expect the model to improve the results in the southern hemisphere, and especially in tropical and subtropical regions. That is where the driving conditions has improved quite a lot, and as well in regions where the topography is really complex, and this link between the synoptical, the mesoscale, and some kind of the microscale effects are mixed up. An example is Ethiopia, where you have a quite complex terrain. We expect the results to improve in some of the areas. As an example, this is, but this is if you have a project in the southern hemisphere, the next version is going to assume that it's going to be closer to the reality.
Great, thank you so much. For IDIS, we've had a few people ask about using the application on different things like their smartphone or tablet or laptop. What is the best way to use the application? And if they're having trouble downloading it, what should they do?
Well, yeah, the application, yeah, it's a web application, so it's not necessary to download it. You can just visit it through the link, globalwindatlas.info, and the best viewing mode to watch it is either desktop or on laptop. But tablet and smartphone is also possible. On tablet, if it is sufficiently large, you will still have the sidebar appearing on the right of the map, and it will still be possible to download files. On smartphone layout, your sidebar is moving to the bottom of the map, and it can still be interesting to use that mode to place points and to get quickly some overview or some details about certain areas. But if you really want to work with the data and you want to download GIS files, for example, or use the plot data, it's most of interest to work on a desktop or laptop.
Okay, and then another question on that is, can they download the layer from GWA and apply it to Google Earth?
Well, you can download the GIS file, which is the TIFF file, and that's maybe something important to notice. So the layers that we see in the application are the TIFF files, which have been processed in order to show the different colors and according to the legend, right? While if you download the GIS file, you get the original TIFF files, which don't, if you open this in the GIS software, you will not see the colors, the fancy colors you see in the web application, but you will get access to the original values of the data. So this is of high interest if you want to do further processing or your own analysis. But to open that in Google Earth, you need to do some GIS processing steps in order to generate the KML, etc., and to upload it in Google Earth.
Great, thank you. And unfortunately, I think we might be out of time for this question and answer session. And for any questions we didn't have time to, we'll connect with those attendees after the webinar. On behalf of the Clean Energy Solutions Center, I'd like to extend a thank you to all of our expert panels today. We had such a great panel. And to our attendees for participating in today's webinar and asking such wonderful questions. We very much appreciate your time and hope in return that there were some valuable insights that you can take back to your ministries, departments, or organizations. We also invite you to inform your colleagues and those in your networks about the Solution Center resources and services, including our no-cost policy support through our Ask an Expert service. I invite you to check the Solution Center website if you'd like to view the slides and listen to the recording of today's presentation, as well as previously held webinars. Additionally, you'll find information on upcoming webinars and other training events. We will be posting this webinar to the Clean Energy Solutions Center YouTube channel. Please allow about a week for the audio recording to be posted. Finally, I would kindly ask you to take a moment to complete the short survey that will appear when we conclude the webinar. Please enjoy the rest of your day, and we hope to see you again at future Clean Energy Solutions Center events. This concludes our webinar.